In the present project, we modeled two fluids in a blender. One was water and the other honey, in order to observe the effects of viscosity in the expected behavior. This was done in order to obtain a better approach when modeling steering tanks that would allow us to obtain a increased efficiency without the need to implement real-life pilots.
The geometry was imported into Star CCM Plus, and the volume mesh of the fluid was generated. With a surface remeasure, a prism layer measure, and a polyhedral measure, the total number of cells was 340,326. Afterwards, the physics models were selected. These are the most relevant. An implicit and steady-state model was selected as the motion of the fluid changes over time. The Eulerian and segregated multi-phase models solve conservation and flow equations for each one of the phases. A volume of fluid model is used for simulating two immiscible fluids. For the liquid phase, a turbulence and kappa omega models were selected for simulation of turbulence with viscous effects. Transition models predict the beginning of transition in a boundary turbulent layer. Turbulence suppression model mimics the effects of transition by removing turbulence in certain regions, and transition boundary distance model calculates the distance from fluid point to the nearest point on a transition boundary. Followed by this, CFD simulations were done for water and honey. The results are presented up ahead.
As can be seen in the water-air interface animation, there is a vortex forming in the center of the blender. Also, in the animation of the velocity of the liquid, we can differentiate the water surface. On the blade's regions, there are water streams that strike with the wall of the blenders. Also, these streams goes up and then is recirculated by the rotational movement of the blades, forming a vortex.
On the other hand, on the interface simulation for honey, the formation of a bigger vortex was appreciated, as well as its effect on the movement of the fluid. Throughout time, the vortex changed in size until the blades had no contact with the fluid. This caused the momentum to stop being transferred to the liquid. Moreover, on the velocity animation for honey, a higher velocity can be appreciated on the ends of the blades. This causes an increase in the momentum transfer rate and a reduction in the time required for the formation of the vortex.
In the simulation of honey, as Reynolds increases, the system enters in a regime which transmits enough energy to the liquid to form a vortex greater than what it wants. However, according to literature, for more viscous liquids, the resistance to flow softens the vortex. In this case, it doesn't occur due to the geometry of the impeller.
Based on the simulations, we can conclude that the velocity profiles were not uniform throughout the fluids. It can also be observed that the impeller does the transfer mainly radially, which means that the transfer between the lower and upper zones of the fluid is low. This means that the impeller is not good for mixing processes, but it's good for dispersing two fluids into two different phases. The differences in the profiles and the behavior observed in the simulations can be explained by the difference in the viscosities from the honey and the water. The behavior is also affected by the type of the impeller, the number of blades it has, the number of impellers present, and the geometry of the blades.